geometry or differentiable manifolds? So what's the title of it?
The official name, I think, is Introduction to Differential Geometry. But
and it's about intrinsic manifolds or submanifolds of Rn, or
no. Usually, they have previously multivariable calculus, and they do everything on Rn and open sets in Rn.
Yeah.
Maybe depending on the time, they will see some manifolds inside our Rn.
Mm-hmm.
And now on this one, it is a complete different approach.
Mm-hmm.
Abstract manifold.
That's good. And it's for which year? I mean, I don't know how to count. You first, is it before or after their bachelor's degree?
Yeah, so this is for the third year.
Yeah.
So this is an 8th semester, so they are in 6th semester.
Of their bachelor's?
Yes.
Yeah, okay. We have something similar here. It's called differentiable manifolds. I think it's probably similar.
Yeah.
I think the big goal of that course is to run cohomology.
Exactly, yeah.
And they used Lee's book. Do you use Lee, or what book do you use?
Oh, I use Lawrence 2 book.
Ah, Lawrence 2. What and 2? The same 2, or so?
Yeah.
Oh, it's his first name. Lawrence is his first name, right?
Yeah, that's the one.
Yeah. So your advisor, right?
Exactly.
Is he still alive, actually?
Who?
Your advisor.
Yeah.
So is he still alive? Oh, Loring, yeah, Loring 2. Is he still alive, or?
Yeah.
Yeah.
And
do you have still contact with him?
Pardon?
Do you still have contact with him?
Yes. Yes. Actually, he will give also a talk maybe in 3 weeks.
Ah.
Yeah.
And that's going to be what? Do you know already, or?
I asked him. He said yes.
Okay.
Let me know when.
Yeah.
So it will be something very introductive, like smart, because I know how he is.
Yeah.
Okay, man. So we're ready.
Good. I'm ready.
So I will let you know after 15 minutes.
Yes. Good.
Share screen.
Oh, thank you very much for the invitation, Andres. So I have to share my screen. Share. Can you see my first slide? Actually, I want to go back here.
Yes, we can see.
Okay. And good. You're admitting people, right? I don't have to do anything there.
Yeah. Don't worry about anything. Just focus on your presentation, and I'll take care of the rest.
Okay, cool. Okay, so
go ahead.
You know, I was asked by Andres to give this presentation. I'm very happy to do this. And I understand that you have some background in differential geometry, but I think I will still review a few things. My talk is about my own field of research, which is symplectic geometry. And the goal is to give you a bit of a glimpse of this field. So I will first start by defining what a symplectic manifold is. These are the basic objects of symplectic geometry. And I will also explain where this comes from, namely from classical mechanics. Then I will talk about 3 different interesting problems in symplectic geometry. So the first one is a famous conjecture by Vladimir Arnold, which is about fixed points of so-called Hamiltonian diffeomorphisms. Hamiltonian diffeomorphisms have a meaning in classical mechanics, namely these are the time evolutions of mechanical systems. By the way, if I talk too quickly, then please interrupt me. Or not if I don't talk clearly or so. So I will talk about those Hamiltonian diffeomorphisms, which play an important role in classical mechanics, and fixed points of those. They correspond to periodic solutions of classical mechanical systems. Then in the second part, or the third part, I will talk about a famous result by Mikhail Gromov, which is about symplectic non-squeezing. So when you have any type of geometry, you can look at maps which preserve your structure. So in the symplectic case, you can look at embeddings which preserve the symplectic forms. And Gromov showed that you cannot do certain things with these embeddings. That's what this result is about. And in the last part, I'm talking about distinguishing structures. So, you know, when you have any structure, let's say you can wonder, if you have an underlying structure, you can wonder how many structures do you find on an underlying structure. For example, if you have just a manifold and you put some additional structure like a Riemannian metric, or now I'm going to talk about symplectic forms, then you can wonder if you have two different symplectic forms, are they the same in some way? And it's especially interesting if you can find forms which are not the same. And that's what I'm going to talk about here in this last part. So let me start with the word symplectic. So what does it mean? Any ideas? Here's the answer. So a symplectic, it's a noun, is a certain bone in certain types of fish, in the head of fish. This one here, the red bone. That's at least what the Merriam-Webster dictionary says, an authoritative source for words. You can find another meaning in that dictionary which has to do with rocks, something from geology. But the meaning we use in mathematics doesn't show up in that dictionary, unfortunately. So what's our meaning? What's symplectic geometry? Well, symplectic geometry is the study of symplectic manifolds and of maps which preserve symplectic forms. So I should explain to you what a symplectic manifold is. Well, a symplectic manifold is a manifold together with a symplectic form. So a symplectic form is a closed and non-degenerate two-form on the given manifold. So I should maybe remind you what a two-form is, and maybe also what the manifold is very quickly. It's some nice sort of space, which locally looks like a coordinate space. So in this picture here, it would be the surface of the sphere, let's say, and locally it looks like the plane R2. And now a two-form on such a manifold, you just told me you know, but anyway, let me just remind you very quickly. It takes a point X in the manifold, and then it takes two vectors which are tangent to the manifold at that point, V and W, and it gives you a real number. Now, what does closeness mean? I will remind you quickly also. If you write your two-form, you can always write it in this way, where xi are coordinate functions. So all omega ij are functions, on some open subset of your manifold in a chart, right? Real valued functions. So you can always write your form this way. And this is the wedge product. So here's a formula for the wedge product. When you write it like this, then the exterior derivative applied to it, d omega, is this sum over here, where now you have a triple wedge product, right? So you apply basically the Leibniz rule, which says you can take d and put it in front of this first factor here, and then you have to make a wedge here in between. If you apply it to this part here, then you will get 0, right? Because d squares to 0. Okay, the triple wedge product is defined in a similar way like this for 2-1 forms. Okay, so that means closeness, d omega is 0. And then there's another condition, namely that it's non-degenerate. And that means that whenever you plug in any vector, when you have a vector v at any point, so that when you plug in another vector w, you get 0 for all other w's, then v has to be 0. It, in some sense, means that your form is maximally interesting or maximally not trivial, right? The 0 form doesn't have this property. Okay, so a symplectic form is a closed, interesting form. Here is a standard example or an important example, namely you take R2n with this form here. So when I'm at the point in R2n, I can plug in two vectors in R2n, and then I take this sum of two terms, or difference of two terms. And I prefer writing it like this. So I write my coordinates as Q1, P1. And then I can write this standard form in this way, where I take derivatives of these functions. Then another example is the sphere S2, which we have here. And here you have also a nice formula for a 2 form, namely this one. Then whenever you have any manifold Q, you can look at its cotangent bundle. So did you learn what the cotangent bundle is? So it's the bundle, vector bundle consisting of all the cotangent spaces. Now the cotangent space at the point is the dual of the tangent space, which means it's all linear maps from the tangent space to the real numbers. And now we can do this for all points, and then we get a vector bundle, and that's again a manifold. You know, the total space of this vector bundle is a manifold. It has twice the dimension of Q. And on this manifold, there is a canonical symplectic form, which I'm not going to write down now for time reasons. If you want, I can do it later. This plays a crucial role in classical mechanics. So in classical mechanics, Q will play the role of configuration space. It's the space in which the position of the system lies, the generalized position. So if you have a particle in R3, Q is going to be R3. And T star R3, you can identify with R3 times the dual of R3, or you can just identify it with R6 if you want. So that is called phase space. T star Q plays the role of phase space. It's the space in which position and momentum lives, or generalized momentum. Then another important family of examples are Kähler manifolds. So a Kähler manifold is a complex manifold. I don't know if you learned, did you learn what a complex manifold is? No. Okay. A complex manifold is defined like a real manifold, but you want the transition maps to be holomorphic and between open subsets of Cn. So you have charts where you go to Cn and then you look at transition maps, and they have to be holomorphic. Okay, now if you have a complex manifold, sometimes you also have a symplectic form on it. And the two have to be compatible in a certain way, which I'm not going to write down. If this is the case, then you call it the Kähler manifold. So this is a whole field in differential geometry, it's called, which deals with these manifolds. And an example for this is CPN. So let me draw a picture of CPN. So if you take n equals 1, then CP1 consists of all lines through the origin in C2. So I have the origin, this one, 0 in C2. So what I draw here is C2. Unfortunately, I cannot draw complex dimensions, so I'm just drawing real dimensions, right? So you should think of each line, each coordinate axis as being C, okay? And now you look at all lines through the origin, through 0, and that's called CP1, the set of all these lines. If you do this in Cn, then you will get CPn minus 1. Actually, C1 you can identify with the sphere, with this thing here, okay, in a canonical way. And on CPN in general, you have a standard symplectic form. In the case of the sphere here of CP1, so complex projective space in one complex dimension, you get the standard form of the sphere, which I wrote down here. Okay. Any questions so far? Okay, so we have examples. What else do we want? Yes, let's talk about where this comes from. Please, if you have questions, please ask. Okay. Okay, so where does this field come from? And the answer is, as I already mentioned, Hamiltonian mechanics. That's a special sort of classical mechanics. Now let's do an example. So let's take a non-relativistic point particle in Rn. Let's say n equals 3. Then maybe you learned in high school that the force F which acts on this particle equals the derivative, the time derivative of momentum. So P is momentum. Momentum is m times the mass times velocity in non-relativistic mechanics. And if you take its time derivative, you get the mass times acceleration, and that's the force, right? Okay, now assume that your force is conservative. So this means that there exists a function u, so that the force is minus the gradient of this function. That's also called potential energy. Okay, this u. Then you can write the equations of motion of your particle as follows. So we have the Newton's second law, right? The derivative, time derivative of the momentum equals minus the gradient of the potential. And then we also have the equation which says that momentum is mass times velocity. Q is the position of your particle. I didn't write it here, but that's what it is. Okay, maybe I should write it here. Q is the position. And P is the momentum. Well, I'm not really good at writing. Okay. Can you?
Yeah. So Q is the position in Rn, and now can you repeat what you mean by non-relativistic?
Yes, it means that momentum is given by the mass times velocity. It is what Newton did in 1600. Right. And then what Einstein did is called relativistic. Then momentum is no longer mass times velocity.
Right.
Now, these are the equations of motion, right? Actually, if you know these equations, if you solve them, you get the path of your physical system, right? It's enough to know these equations. It determines everything. If you know the initial position and initial momentum, and you know these equations, you solve them, then you know how the system evolves. Now, you can rewrite these equations in this way. So remember, we had the standard symplectic form here, right? In R2n. And the Hamilton's equation says that when you plug in the derivative of your path in phase space in R2n, right? So it consists of the position and momentum. If you take the derivative of this path and you plug it into your standard form, you get the derivative of your function, of a function h at the right point. And this function h is called Hamiltonian or Hamilton function. And it's also called the total energy. So it consists of kinetic energy, this one, and potential energy. Hamilton wrote down these equations in the 19th century. Now, here's an example. We take the potential energy given by this quadratic expression in position. Then the Hamiltonian is given also by a quadratic expression. And Hamilton's equation, say this equation here, this is Hamilton's equation. So Hamilton I'm not going to derive this, but it follows from the form, for the symplectic form, for the form I gave you, and from this equation here. It's two-line derivation or so. Here I use, the complex notation, right? I can identify R2 with C. That's what I do. This is the imaginary unit. And you can solve this equation, right? Namely, the motion of your system is given by rotation by E, by this minus t, right? The angle minus t. This is what this notation does, right? You rotate in R2. For each factor of R2, you write R2n as R2 times R2 and so on, right? Okay. Now, you may wonder, okay, we had something simple, namely Newton's second law, and then we rewrote it in a complicated way. Why is this good? And the answer is, this formalism here, Hamilton's equation, this works much more generally than just for a particle in Rn. You can describe most mechanical systems with this formalism. And in a general situation, you will have a path in the cotangent bundle of configuration space. So configuration space is Q, that's where the position, or the generalized position of your system lives, and then you will have a path in the cotangent bundle. And you can use the canonical symplectic form of the cotangent bundle to write down the same equations here, and that determines your motion of the system. By the way, I want to give you an example of another mechanical system, namely this one. It's called a rigid body. It's also called a cell phone, but physically seen, it's a rigid body. It means that, you know, you cannot bend it. It doesn't. It stays the same, right? It stays the same in shape when I try to bend it or rotate it. And for example, this system, in this case, the configuration space, the generalized position space is R3 for the center of mass times SO3, the rotational group SO3, because you can hold your phone like this first, and then you can rotate it in any way, and that gives you a rotational position. And that's interesting. You know, SO3 is not so easy to understand as R3. And you can still use the same equations here to describe the motion of a cell phone when you throw it or so, how it rotates, for example, or any stone. You can take any stone and describe the motion of it. Now you can see that this is where symplectic geometry, you know, it comes in. Namely, here we have the standard symplectic form, right? And in general, we will have the canonical symplectic form on the cotangent bundle. Okay, that's where symplectic geometry comes from. Any questions? Now, I want to talk about 3 questions which people in symplectic geometry have studied. So what I talked about here goes back to Hamilton. He lived in the 19th century, and now I want to shift 100 years. I'm going to talk about the 20th century, the second part of the 20th century. And the first thing I'm going to talk about is a famous conjecture by Vladimir Arnold. So let's state this one. And it's about so-called Hamiltonian diffeomorphism. So I have to explain what it is. So let's start with a symplectic manifold. Okay, I say the same thing twice. Anyway, I fix a symplectic manifold. So what's a Hamiltonian diffeomorphism? So for that, I have to first define the Hamiltonian vector field generated by a function on the manifold. So let's take a function f on the manifold, real valued. Then we define the Hamiltonian vector field xf by this formula here. This is the derivative of f. When you plug in a vector field into a 2 form, you will get a 1 form. So it makes sense to say that we ask the vector field to satisfy this equation. And in fact, there's a unique such vector field. That's because the 2 form omega is non-degenerate. Good. So we defined the vector field. Now, when we have a time-dependent function h, we can do the same construction for each time. And then we get a time-dependent vector field. Now, you told me that you learned what a flow is, right? That's what we do now. We take the flow of this time-dependent vector field. If you want me to repeat, I can tell again what the flow does. It solves a certain ordinary differential equation, right? So maybe I can just make a picture. See, this is what the flow does. You start with a point x0, and then you look at the path, which is tangent to your given vector field. It should be tangent. I should be more tangent than it's in my picture, but I'm not really good at drawing here. Let's draw again. So here's a point. Now look at the path like this, which is tangent to my vector field. This is x, h, t at x0, and I do this for all times. I always want to be tangent. And that defines my flow. Okay. So this would be x of t, and x of t is phi h t of x0. Okay. Now, a Hamiltonian diffeomorphism is a time 1 flow, which we get this way. And you should make sure that the flow is well defined for all times and surjective, and for all points in your manifold. For example, if you take a compact manifold without boundary, then this is the case. For example, S2, the sphere, which we just had before, right? Okay, so this is what the Hamiltonian diffeomorphism is. It's a time one map, which we get in this way, the time one flow of a time-dependent function, h. For example, if you take the harmonic oscillator, we have this quadratic function here, and the flow does exactly what I explained before. You solve the differential equation, Hamilton's equation, right? And you get rotation by minus t in each vector R2, right? Good. Now, another example is when you take the sphere with the standard symplectic form and you look at the height function, then the Hamiltonian flow for this is rotation again, but now in R3. You rotate your sphere like this. Good. Now we have examples. By the way, Professor Pedrosa, he studied Hamiltonian diffeomorphisms in his work. So, the Hamiltonian diffeomorphisms are a subset of the set of all diffeomorphisms, but in fact a subgroup. And Pedrosa studied this subgroup. Now, I will formulate a famous conjecture by Arnold from 1965. Namely, it says when you have a closed symplectic manifold, so closed means compact without boundary, then if you have a Hamiltonian diffeomorphism, it has at least crit m fixed points. Now, this number crit m is the minimal number of critical points of a smooth function on your manifold. Let's look at an example. And before I do that, let's mention that fixed points correspond to periodic orbits when your Hamiltonian function, time-dependent function, is periodic in time. Let's say with period 1. Then fixed points of the time 1 map correspond to periodic orbits, periodic solutions of Hamilton's equation. The one which says that the derivative of your point x in time is given by the vector field xht at that point where you are. Now, this is interesting because it describes the evolution of a mechanical system, as I explained before, for a particle in R3, but it's more general. And periodic solutions of mechanical systems were investigated by mathematicians. For example, you can wonder whether the solar system is periodic, right? Do we come back to the same situation after a fixed period of time, maybe a very long period of time, but you can ask whether we will come back to a situation where all the planets have the same positions as in the beginning, and all the velocities are also the same. And that's maybe very difficult to answer, or it's not likely that this happens, but now when we do, it is on a closed symplectic manifold. So the the solar system doesn't correspond to a closed symplectic manifold. Then we can ask not just does this now is our given system periodic? That's maybe too much to ask, but you can ask, is there any periodic system, right? Is there any periodic? Is there any initial choice of positions and momenta, so that after a fixed time like time 1, we'll come back to the same positions and momenta? And that's this conjecture by Arnold. He gave an expression for how many such periodic solutions you should have. Now, in fact, if you take S2 with the standard symplectic form, then this conjecture was proved by Simon and Nikishin in the 70s. So in this case, this number here, minimum number of critical points, is 2. Does anybody know why? Does anybody know why we have at least 2 critical points when we have a smooth function on the sphere, on S2?
They know, come on. One of you must answer this.
Both poles, right? North and south pole.
Yes, that's correct. So when we take the height function, then the north and the south pole are critical points. Why? Why is the north pole?
The time plane is like totally flat.
Yes.
With a height function.
Yes, correct. But in general, see, maybe we take another function, which is not the height function. What sorts of points are always critical points? Do you know any sort of point which is always a critical point? There are two, which are always, namely, a maximum is always a critical point and minimum, right? And when you have a smooth function or just continuous function on any compact set, you always have a maximum and you always have a minimum, right? So we always have two critical points at least. And in the case of the sphere, if we take the height function, then we have only two critical points, so we don't have more. So this minimal number of critical points is 2. And Simon and Nikishin proved that when you have a general Hamiltonian diffeomorphism, it will have two fixed points. So if we take the height function, then the fixed points are the north and the south pole, right? Because the Hamiltonian diffeomorphism is given by rotation. But this is about a very general Hamiltonian diffeomorphism, not just the height function of the sphere. And the conjecture says we still have two fixed points. And that's what Simon and Nikishin proved for the sphere. Now, the motivation for this bound, for this crit M, is that when you have a time-independent function h, then the critical points of this function are zeros of the vector field xh, right? Because, see, this vector field xh was defined like this. If you plug it into, let's make it an xf. If you plug it into omega, you get df, right? So now if you have a critical point of f, so df of x equals 0, then xf also equals 0, because omega is non-degenerate. So we have a 0 of the vector field, but then if we take the flow, this point doesn't move. If you have a 0 of the vector field, you have a fixed point of the flow. And that's why Arnold conjectured that we have so many fixed points for a general Hamiltonian diffeomorphism as we have critical points for a function at least. But it's very important that this is a conjecture about all Hamiltonian diffeomorphisms, also those which do not come from a time-independent function, and those exist. So sometimes you cannot find a time-independent function which generates your Hamiltonian diffeomorphism. Any questions about this? Okay, now, actually, this precise conjecture is still open, but some version of it was proved by Fleur and others later. So Fleur developed a certain homology called Fleur homology. It's a homology theory in the sense of algebra. I'm not going to explain this. It uses a lot of analysis, and using this, he proved this, not exactly this bound on the number of fixed points, but a certain bound involving the Betti numbers. It involves the sum of the Betti numbers of M. It's not so important exactly what the bound is. In particular, he proved that there is at least one fixed point. Now, this conjecture about Hamiltonian diffeomorphisms, shows a certain important symplectic phenomenon, which is called rigidity. So rigidity means, in general, this is not a symplectic thing in general. It means that you have a certain structure, for example, a symplectic structure, and there is an underlying structure. So in the case of a symplectic structure, you could take the underlying structure of a smooth manifold, right? And then you can wonder, when you have a property, which holds for one of the two structures, does it also hold for the other one? So for example, you can ask, when I have a diffeomorphism which is isotopic to the identity, so I have a whole family of diffeomorphisms starting at the identity and I end up at diffeomorphism. You can wonder whether it has a fixed point. So that's a property of diffeomorphisms which are isotopic to the identity. What do you think if you ask this question for a smooth manifold, let's say without boundary and compact? do you have a fixed point when you have a diffeomorphism which you can, if you want, continuously move to the identity? Does it have a fixed point? Well, for example, if you take the torus, so not the sphere, but the torus, right? The thing with the hole, this thing here. Now, can you, if I take a diffeomorphism, so some smooth map from the torus to itself, which is also, invertible, and the inverse is also smooth, and I assume that this diffeomorphism, it comes from a whole family. It starts at the identity. Does it have to have a fixed point? Well, not really, right? I can just rotate my torus in this way, like this, right? By some degree. So there's no fixed point. However, on the torus, you also have a symplectic form. It's given by a similar formula like the one for the sphere. And now the Arnold conjecture says that on the torus, if you have a Hamiltonian diffeomorphism, so it's also isotopic to the identity, right? Because it comes from a whole flow. So if you have such a diffeomorphism, it does have a fixed point. That's the conjecture. And if you just say one fixed point, that's proved. Okay. So Hamiltonian diffeomorphism behave differently from just diffeomorphisms which are isotopic to the identity, or otherwise spoken, symplectic geometry behaves differently from smooth geometry. Okay. And that's what rigidity means. Okay. Now, any questions? Now let's go to something else, unrelated. Yes.
So let me just to make a comment for my students. So Fabian draw the torus because he's thinking of symplectic. But you can also keep in mind, we studied a few weeks ago Lie groups. Remember that on the Lie group, we were able to find vector fields that do not vanish anywhere. So in that sense, if you forget about the symplectic, just think about the circle. We studied the circle and the rotation. Okay, so that's why we spend so much time on Lie groups. But here, this is one of the features, but the torus, because it is symplectic, that's why Fabian is making this example. But to relate it with the class, think about a Lie group. And even simpler, the circles. Sorry, Fabian, go ahead.
No, thank you for clarification. Now, let's move to some different topic. That's the second highlight I want to talk about of symplectic geometry. It's a theorem by Gromov. Namely, so I should explain first, what it means for a map between two symplectic manifolds to be symplectic. Namely, it means, first of all, it's smooth. And then if you pull back the second form here by your map, you should get the first form. And pulling back means you plug in the derivative of your map into the form twice, right? Okay. Now, it happens that when you have a symplectic embedding, it preserves volume if you do it in R2N. If you have any open subset of R2N, and you look at the smooth map, which is also an embedding, smooth embedding, from an open subset into, again, R2N, then it preserves the standard volume in R2N. That's called Lewis' theorem. It's from the 19th century. Now you can wonder, how much do symplectic embeddings differ from volume-preserving embeddings? First of all, not every volume-preserving embedding is in fact symplectic, but that's easy. It's something about linear algebra. But then you can wonder, what sorts of things can I do with volume-preserving embeddings, which I cannot do with symplectic embeddings, for example? And Gromov's non-squeezing gives an answer to this. So, you can, for example, embed a ball of any radius, a ball in R2N, into the so-called symplectic cylinder. So the cylinder is the disk in R2. So this is really two-dimensional, and then I have the extra dimensions. Unfortunately, I cannot draw more than 3 dimensions, let's say. So this should be R2n minus 2 in this direction. So for example, it should be two-dimensional if I start with 4 dimensions here. I have the same dimensions here and there, okay? So you can take your ball and squeeze it into a cylinder like this so that the volume stays the same, okay? However, a famous theorem by Gromov is that when you take, again, a radius bigger than 1, you cannot symplectically embed a ball in this way into this cylinder. Again, this is an example of rigidity. So this time I compare symplectic structures to volume forms. So this notion of a volume form, if you don't know what that is, you can also compare it just to volumes of sets, let's say. Now, you know, you can look at properties which hold for volume structures. So for example, the property that you can embed a ball like this, right? And then you can wonder whether these properties also hold for symplectic structures, and the answer is no in this case, right? You cannot embed in a symplectic way. Again, this is an example of rigidity, therefore. And I want to make an analogy. See, this fact that you cannot embed into such a cylinder means that the first 2 coordinates, Q1 and P1, cannot be restrained more than what I have here, right? Here I have, if I look at only the first 2 coordinates, I have a disk with radius r in R2, right? And you cannot map this whole ball in such a way that this disk will be shrunk. And that's a bit like the Heisenberg uncertainty relation, which tells you something about standard deviations for the position and for the momentum, for each coordinate of them. Now, this theorem by Gromov has an important consequence, namely, it's the theorem by Rierschberg and Gromov. Here you can see a picture of Rierschberg. Namely, it says that the set of all diffeomorphisms which preserve the symplectic form is C0 closed in the set of all diffeomorphisms. Did you hear about C0 distance or the C0 norm? So when you have functions from R to R, let's say continuous, or maybe let's not make it R, let's make functions from the closed interval 0, 1 to R. Did you hear about the supremum norm? So when you take 2 functions, you can look at, or just 1 function, I can look at the norm of such a function, C0 or supremum norm. It's this thing here. It's the supremum of the absolute value of my function, right? Over all points. And that's how this C0 topology is defined. So first, you know, at least in coordinates, you can look at this norm, and then you look at the corresponding distance, and then you look at the corresponding topology. That's what I mean here when I say C0 closed. And you should do it in a local way. You should only take as domains compact subsets. So maybe I should say a bit more. If you take a compact manifold, then you can really do this for the whole manifold. Otherwise, you have to be a bit careful what you mean by C0. And you know, this gives you a topology. In particular, you can look at sequences. And C0 closeness means that when you have a sequence of such diffeomorphisms which have this property, and it converges. So if you have a whole sequence of such, which converges with respect to this norm here in coordinates. So as I goes to infinity, it converges to something. And these lie here. So I start with diffeomorphisms which have this property. They preserve the symplectic form. They're called symplectomorphisms. Then the statement is, this is the statement, that the limit also lies here. This should be the statement. Okay. By the way, this is a group a subgroup of the diffeomorphism group. It's called the simple ectomorphism group. It contains the Hamiltonian diffeomorphism group. So the set of all Hamiltonian diffeomorphisms, which I talked about before, right? That's, you know, that's maybe an important feature of it. So another reason why this group is interesting is because in classical mechanics, it corresponds to canonical transformations. So simple ectomorphisms play the role of canonical transformations under which Hamilton's equation stays the same. So the description of classical mechanics stays the same. Now, you know, this is very maybe surprising, because when you look at the equation which says that you have a simple ectomorphism, it's a first order partial differential equation. Did you hear what the differential equation is? It's an equation which involves derivatives, right? And first order means there's only a first derivative, no second derivative. And that's what I have here. I take the derivative of phi and I plug it into my omega twice, right? And then I want an equality here. So I have an equation. And now, when you have a sequence of solutions of a first order differential equation, and you know the sequence converges in C0. So here, I mean in C0. Then in general, the solution, the limit will not solve the same equation. It's a very strong statement to say that the limit solves the same equation like my sequence. If you have a C1 convergent sequence, then yes, then it solves it as well, but C0 not. And here's an example of such a sequence, which so that the limit does not solve the same equation. You take the following, you take the equation in one dimension, the derivative of phi equals 1, let's say of phi I, right? So I can take a zigzag like here. It's not really differentiable in this point here, but I don't care. You can make it, you know, you can make sense of the derivative anyway, okay? And then this is the first one, it's a zigzag. Now I take the second one. It's still a zigzag, but a smaller zigzag like this. Okay, and the next one is going to be even a smaller zigzag like this one. So the absolute value of the derivative is always 1. And they converge. To what do they converge in C0? Any ideas? I mean, even if you don't quite understand what C0 convergence means, but what do these functions converge to, if you look at them?
To a line problem?
Yes, just to a straight line like this. It should be straight. And the derivative of this function is 0, right? Everywhere. It doesn't solve the equation, right? So there's no reason for having the equation be solved if you know it's solved for each member of the sequence in the limit, if you have only C0 convergence. Okay, so this is a striking result that this is true when you look at this particular equation. And again, this is an example of rigidity. In this case, you know, the rigidity comes from having some extra symplectic information. So if you just look at differential equations, then the property does not hold, right? That the limit solves the same equation. But if you have an equation coming from symplectic geometry, namely this one, then you have this property that the limit still solves the equation. Any questions? Now, I want to mention, so first of all, I want to say, you know, this is an application of this theorem. I'm not going to explain how you can use this theorem to prove this other theorem. You know, it's not one page, it's more. You have to say more, but it does follow from this theorem. Now, I want to talk just about one result of myself, just to give you a feeling of what symplectic geometries do nowadays in 2021. Okay, actually, this is something I proved 10 years ago. So it improves Gromov's non-squeezing. Namely, my co-advisor actually asked a long time ago. He didn't give me this as a PhD thesis, but a long time ago he asked the question whether there's any neighborhood of the unit sphere, this is the unit sphere in R2n, which symplectically embeds into the symplectic cylinder. Right? This was, remember, this was B2 with radius 1 times R2n minus 2. You know, the ball of radius r, if r is bigger than 1, is a neighborhood of this sphere. So he wondered, well, okay, the ball does not embed by Gromov's non-squeezing, but is there maybe a very, very thin neighborhood of the sphere, right? Which does embed in a symplectic way. So what do you think? Well, so this is for n at least 2. No, the answer is no. And actually, you know, you can take any product of spheres and then a neighborhood of that, and the answer is still no. That's a result I proved together with Jan Svoboda some 10 years ago. So here I have integers which are all at least 2. And I look at these spheres, right? 2n minus 1. So, for example, you can take S3 here, 3-dimensional sphere. Take a product of S3s or S5s if you want. Okay? Anything higher than S1, it should be odd-dimensional. If you take now a neighborhood of this product in R2n for the right n is this sum here, then you cannot symplectically embed this into the standard symplectic cylinder. And that's something I would call skinny non-squeezing. Skin means your skin, you know. It's very thin. So it's a thin sort of non-squeezing. Any questions? Please ask. Now, do I still have some time to talk about the last highlight of symplectic geometry?
Yes, so in 2 minutes, you will reach your 50-minute warning that you asked.
Yes. Okay, good.
Continue, thank you.
So, it's about the question, when you have two symplectic forms, are they isomorphic? This is a question you can ask in any category, with any sort of structure, right? If I have two different structures, are they actually the same? Like if you have groups, right? You can ask, given two groups, are they isomorphic, right? We can ask this for symplectic forms. Or more precisely, when we have a fixed manifold, how many isomorphic classes of symplectic forms are there on this manifold? People usually say isomorphism. I like isomorphic classes, if you don't mind. So there's a theorem by Moser, who Moser is no longer alive, actually. Gromov and Zehnder and who else? Who did I cite? I have to think.
Elias
Elias-Berg, yeah, right. Elias-Berg, Gromov, and Zehnder are still alive.
Hamilton, Newton.
No, Hamilton, 19th century. And we had also Arnold, he also died a few years ago, but Moser died a few years ago, 20 years ago also. Anyway, so Moser asked, or proved, when you have two symplectic forms on a closed, so compact without boundary and connected real surface. Real surface means two-dimensional manifold. So two symplectic forms on such a surface are isomorphic if and only if they have the same total area or volume, right? You can take your symplectic form and integrate it over your surface. It's oriented in a canonical way. And then you will get a number, and that's the total area. Now, that's a form of flexibility. See, it says that when you, instead of just looking at smooth manifolds, you add some structure, namely that of a symplectic structure. You don't gain any more information really, except for the total area. So it's not 100% flexibility, but almost. There's only one real parameter which we gain. Okay. Good. Actually, locally, all symplectic manifolds of the same dimension look the same. That's a theorem by Darboux from the 19th century. So locally, they're all isomorphic in all dimensions. So again, this is a sort of flexibility. So they all look like R2n with the standard form, which I explained in the beginning, right? Locally. However, there's a famous result by Gromov again, which is that there is a symplectic form on R2n for n at least 2. So we have at least 4 dimensions, which does not come from the standard form in this way. So you don't obtain this form omega as a pullback via a smooth embedding of R2n into itself of the standard form. In particular, this form is not isomorphic to the standard form, so there's no diffeomorphism which intertwines the two forms. But even stronger, you cannot get it via an embedding. Okay. This result is again, it expresses a certain form of rigidity, right? You have more information when you also know the symplectic form than if you just know the smooth manifold, namely R2n. The proof of this result and the other rigidity result, which I mentioned, uses what's called holomorphic curves. That's something Gromov introduced 35 years ago. And it's widely used in symplectic geometry. It has to do with holomorphic functions from an open subset of C to C, but it's more general. It's in higher dimensions also when your target is a symplectic manifold equipped with a so-called almost complex structure. And these curves play a very important role. And what I talked about when I talked about the Arnold conjecture, I said, you use Floer homology. So that Floer homology is based on a similar sort of map, namely not holomorphic maps, but it's based on solutions of Floer's equation, which is some version of a holomorphic map. Yeah, that's basically what I wanted to talk about. And maybe Andres can tell you what this picture is about. Or maybe some other time. So I hope that I gave you a bit of an impression what symplectic geometry is about. Old symplectic geometry from the 19th century and newer symplectic geometry. And please ask questions if you have.
Thank you. Thank you, Fabian.
Thank you.
Well, you're welcome.
What is camel man?
Okay, so there's a famous result in symplectic geometry, the Camel theorem, which says that when you take R2n with n at least 2, so R4 for example, and you take away a wall is something three-dimensional, right, in R4, something of codimension 1, so 3 dimensions in R4. You take out R3, but you make a hole in R3. This is a hole, right? Now I have a space, which is R4 without this wall with a hole. And then you put a ball on the left-hand side, the ball we had before in 4 dimensions, which has a radius bigger than the radius of the hole. Then you can wonder if you can push this ball through the hole in a symplectic way. So for each time, you want to have a symplectic embedding of your ball into, again, the same space, right, without the wall. You want to stay away from the wall with the hole. So at some point, it will have to go through this hole, right? So it looks, maybe it could go like this, like the camel, right? This is part of the ball and the other part is the other side of the camel, right? So the question is, can you do this? And the answer is no. That's the camel theorem. It's a variant of the non-squeezing theorem, but it's not the same thing because now you're moving in time, right? When you do the non-squeezing, you have a fixed time, you just map it. But now I move, I have a whole family of embeddings, right? And the reason why this is called the camel theorem is that in the Bible, there's a saying, namely that, now I'm not sure if I can get it right. Rather would a camel go through the eye of a needle than a rich person to heaven. So, a needle is this thing which you use to saw, right? This thing here. Not good at drawing. You lose some thread, right? And then you can saw. And now this is the hole of the needle. I made it very thin. So rather would a camel go through this hole here than a rich person to heaven. And that's why people call this the camel theorem, because they like this quotation from the Bible. So maybe you notice that in symplectic geometry, this difference between rigid statements and flexible statements is important. So the question is, do you have more information when you have this new structure, symplectic form, than if you only have a smooth structure, or if you only have a volume preserving structure? Or when you look at differential equations, when you now know that your differential equation comes from symplectic geometry, can you say more about it than usually? So that's an important way of thinking in symplectic geometry. And also in other fields. See, when you have, did you take a course on complex analysis in one variable? Did you have a course like this? So did you?
I'm on it. So.
Oh, we didn't. But I don't know. Wait, what's your name again? The other person.
Salvador.
Salvador. So you did, right?
Yeah, a sort of a course on calculus on complex variable.
Yes. So did you learn about Lewis' theorem from complex variables? It's a different one than the one I mentioned here. It's also called Lewis' theorem. So when you have a holomorphic map from the whole plane C to C, and you know that it doesn't grow, it's bounded, right? Can you say anything about it?
Must be constant.
Yes, constants. That's Lewis' theorem, right? So this is a bit similar, right? It's also rigidity. So the extra information you have by knowing that it's holomorphic restricts your function a lot. Holomorphic functions are smooth. And it's easy to write down a smooth function, which is not constant, but is bounded on C, right? You can, so in one dimension, real dimension, you can do this like this, right? So you can make it like this, a bump function, right? You have a lot of choice. But if you say now we have this extra structure, namely a complex structure, and we have the assumption that our map is holomorphic, then all of a sudden the situation changes completely, right? That's also rigidity. A different sort of, has nothing to do with symplectic geometry, but it's also rigidity. Of course, symplectic geometry is a big field, and I gave you 3 examples of questions people are interested in. So it's not I didn't give you an exhaustive list, right, of all things people are doing. But there are also variations. So, the first question I talked about, the Arnold conjecture, is something I didn't work on exactly, but I worked on a variation of this. So I didn't look at fixed points of a Hamiltonian diffeomorphism, but I looked at so-called Levi fixed points. And then, also the embedding question, you can ask variations of that. So for example, I looked at pre-symplectic embedding. So there's a generalization of the notion of a symplectic manifold where you don't ask that the form is non-degenerate, but it has to have constant co-rank, whatever that means. And then you can again ask embedding questions, right? I looked at that question, for example. Or, there are other variations. And then there is another field called contact geometry, which is related. So there you don't have a 2 form, you have a 1 form, and then it's interesting to compare the 2 fields also. Maybe I can also tell you a bit about fields which symplectic geometry is related. I maybe mentioned in the beginning classical mechanics, but it's also related to something called Poisson geometry, and Kähler manifolds are mentioned, so it's related to Kähler geometry, which is related to algebraic geometry. And in fact, in symplectic geometry, we look at certain invariants, namely, well, amongst others, we look at the so-called Gromov-Witten invariants, and those are also analyzed in algebraic geometry from a different point of view. It has a lot of interaction with other fields. Also, in physics, there is a field called string theory, and those Gromov-Witten invariants play an important role also in that theory. So that's again related to symplectic geometry. So symplectic geometry is then related to modern sort of physics. By classical mechanics is maybe old physics, but string theory is a modern sort of physics.
Fabian, for this result of Rohmov, the punchline is Lagrangians of manifold. I don't remember that. Or
how do you construct this symplectic form? You find an immersed Lagrangian,
yeah,
which is exact.
Yeah, exactly.
And then you wiggle, and then it's embedded. And then you take you thicken it. You make it lie in the sphere, and then you take out one point in the sphere and you thicken it, and then you get R2n again.
And that's how that's the punchline for that. Okay.
But there was some so you know, there were some so the main ingredient, I guess, is that you can actually make your Lagrangian embedded if you change your symplectic form. You start with an immersed one, but then you wiggle and you can make it embedded with a different symplectic form.
Yes, yes. I just what I
I
don't
forgot the
remember
details
very
as well, actually. I must say.
Now, also, when you were describing the Hamilton's equation,
Yep.
I don't know if you mentioned the cell phone. You say, okay, or a rock. You throw the
Yes.
rock, and then Hamilton's equation will describe. But did you mention the Hamiltonian or the energy?
Yeah. Look at this. So here is Hamilton's equation again, right? First I had Newton's equations, or equation, this one, and then I also had the one which says that momentum is given by mass times velocity, right? And here is Hamilton's equation again.
But,
So it says, actually, maybe I can write this down again, right? It says x dot. Now that I introduced those Hamiltonian vector fields, you can rewrite this. It says x dot of t equals x ht of x of t.
but I mean, for the particular case that you mentioned, that you have the rock or the cell
Yes.
phone in free space and you throw it away.
Yes.
And then, what is the h?
Well,
It's not nothing, right?
I tell you. So the position consists of two things, right? Of center of mass position in R3 and the rotational position, right? As I said, you can rotate it.
SO3, yes.
And then momentum P consists again of two things. It consists of the total momentum of your rock, and linear momentum, right?
Okay.
The momentum of the center of mass.
Yes.
But then it also consists of angular momentum, if you want, rotational momentum, right? That's the one which corresponds to your rotational position. And mathematically speaking, it's a covector, right? You look at the cotangent bundle of your configuration space. So I will have the cotangent bundle of SO3. And in SO3, I have my generalized position. And now the covector above a generalized position, that's momentum.
But I mean, oh, yeah, okay.
And then
I was having trouble because I didn't see the force of gravity, but it will be encoded in the angular momentum and linear momentum, right?
yes, so the force of gravity only acts on the center of mass.
So it will be encoded in the momentum.
Yeah, well,
Not on H.
no, that's going to be encoded in this U, the potential, right? The force of gravity.
Oh, that will be, so the H will be that where gravity will be on U.
Yes, and there will only be, see, when you look at this U of Q, you will only have the position of the center of mass here.
Yes, right, yeah.
Now you can, of course, also make a torque. Torque is what you do when you rotate it, right? So you give it a push, you have a force like this here, and you have a force like that over there. That's called a torque, or moment of force. And then you will also have you will have an extra term here, right? Or you would have an extra force, right? But if you have the simplest situation, you will have zero. You will be zero, and that's already interesting. Or you can make it gravitation, but let's make it zero actually. So we only have kinetic energy. but it also involves kinetic energy coming from angular momentum. And then you can wonder what these bars mean when you have angular momentum. And the answer is, it's your, now what's this tensor called? Now it escapes my mind. I know what it is in German. I forgot what it was in English. It's not called the rigidity tensor, but something like that. The inertia tensor. See, you will have the inertia tensor. I think that's what it's called. It's something from classical mechanics. It expresses how your mass is distributed in your object. So the further away mass is from the center of mass, the more it contributes to this tensor. I mean, I don't want to go maybe into too many details, but the main point here is that this formalism, namely this equation, Hamilton's equation, describes extremely general systems.
Yes, yes, no, thank you. Yeah,
That's
I mean,
point.
I just wanted to,
yeah.
Because this is the general setting, but then you mentioned the rock that you throw it away, and just wanted to know what's the corresponding age.
Yes, yes, it's a good question. And, you know, it's some calculation. It's not, you cannot just see it, that what exactly this kinetic energy is, you know.
Right, thank you. So I don't know if students have any questions or comments. Daniel and Salvador.
Was it understandable, by the way?
I have a kind of history question.
Yes, sure.
Well, the Darboux theorem is telling that there are not local symplectic invariants.
Yes.
So before Darboux, were the people studying like symplectic invariants or something like that?
No, I don't think so.
Right.
So first of all, you know, usually the way a field evolves is not linear at all. So I presented it in a quite linear way, I think. Starting with Hamilton's equation for a particle in R3. And that was actually not how it evolved. It's actually always the same. I think it's true for many subfields of mathematics. So my understanding is that symplectic geometry was maybe invented by Lagrange or so in the 18th century. And he looked at something called a symplectic quotient, which in physical terms is reduction of degrees of freedom. So it's a complicated construction which he looked at. Instead of looking at the simplest mechanical system, namely particle in R3, he looked at something complicated in the context of a solar system, you know. Now, I think people in the 18th and 19th century were interested in solving Hamilton's equation. Maybe since Hamilton came up with it, or maybe before it, they were interested in solving Newton's equation, right? So in whatever sense, you know, they wanted to have an explicit formula or maybe say something about solutions, at least that they exist or so. I think that's what people were interested in. And then global symplectic questions. So not about, you know, solving something is a local thing. You know, you have a differential equation. It only depends on the neighborhood of where you are, right? But those global questions about if you have two symplectic manifolds, are they the same or so? That really is a global question because, you know, because of Darboux's theorem. So that's something which started with Gromov's paper from 1985, I think. These global questions were addressed then. Plus, maybe the other global question about, you know, having fixed points, that's something Arnold started, and then I told you about the result by Simon and Nikishin from the 70s. But the question really about having, like, whether or not two forms were isomorphic, I think, now I'm not sure, but I think basically nothing was known before Gromov. I mean, you know, as I said, Lewis theorem says, every symplectic embedding preserves volume. So in particular, you can look at the total volume of your symplectic manifold. So you can do this also if you're in higher dimension. I didn't tell you how, but you can take your 2 form and take its wedge product with itself n times, if you're in dimension 2n. Then you get a volume form and you integrate it, and that gives you a real number. Now, if you have 2 symplectic manifolds, which are symplectic or isomorphic, right? There is a diffeomorphism which intertwines the forms. Then they have the same total volume. That's a version of Lewis' theorem. So that's something people were aware. I mean, I'm not sure if Lewis thought about this way, right? He just understood that. Maybe he thought about it in terms of classical mechanics, right? He understood that canonical transformations, they would call them then, preserve the volume of phase space. That's what he understood. And he didn't wonder maybe about manifolds at all, because probably he looked at it locally, right? But let's say, people like Arnold or so, they may have thought about global questions. Like they would have been aware, at least Moser, right? I mean, Moser classified 2-dimensional real symplectic manifolds, compact without boundary, this way, right? So around that time, people would look at this question. So this was I don't know, in the 60s maybe, when Moser proved this. I'm not sure exactly when. Now, it's especially interesting when you can show that 2 structures are not the same, right? And I think that's the first interesting example of that sort was by Gromov, I think. But I don't want to say I'm sure, because I didn't study the history of symplectic geometry enough to say this for sure. But I wouldn't be surprised if he was the first to say that 2 symplectic forms are not the same in an interesting setting, right? Not just using volume.
Okay.
Yeah. Moser result is from the 1965.
Ah, okay. Yeah. Like the Arnold conjecture, then. Yeah.
Yeah. Now, because so also you just mentioned Simon's result, because that one also is
70s. It's from the 70s.
Because the approach is volume preserving diffeomorphisms.
Yeah, so Rieschberg, I think Rieschberg did it then for general surfaces.
Right, and that was what I wanted to ask you. Do you know that? I mean, I look it up because for the other surfaces, exactly, you need more techniques than the one that Simon.
Yeah, I didn't actually look at the proof.
And it is attributed to Eliasberg, but I have no clue if that's true.
So you think he didn't give all details, or?
I mean, the paper is not available because it is an old journal.
In a Russian, in a Soviet journal, right?
Exactly.
Yeah, right. But you could just email Rieschberg, then you would find out.
I think I did, and he told me he doesn't have the paper.
But then one of his students has it or something. No?
And yeah, because so one of my undergrad students last year, so he actually looked at Simon's paper because to prove Arnold conjecture for volume preserving diffeomorphism.
Yeah.
And for the sphere, they use some the Euler number vector fields.
Yeah.
And so that I knew, but I wanted to know what were the techniques for the other surfaces.
Yeah.
I was aware of Eliasberg's result, but I have no clue.
Yeah. Yeah.
About the techniques and all.
So he found out, your student, did he find out eventually who is it's you or so? Or?
So I mean, his work was limited to Simon's paper.
Yeah.
For the sphere. But for the other surfaces, we have no idea.
Okay. Yeah.
Because also, I mean, this paper from Eliasberg was holomorphic curves. So I don't know what are techniques he used to prove that.
I don't know. Probably something elementary, but I don't know.
And very clever.
Yeah, yeah.
Right. So I don't know if our students have any more questions.
So by the way, I'm curious. So, or yeah, do you have questions too?
Shoot, Fabian?
I was wondering, so you're both in your third year, Andres said, right?
Well, Salvador is in third year and Daniel, he's a senior, he's in his fourth year.
Oh, okay. And are you interested in going in the direction of differential geometry, or? I mean, are you going to do a master's maybe in differential geometry?
Yes, I am.
Yeah.
Actually, I'm doing my senior thesis in symplectic geometry.
Oh, that's good. Oh, so then maybe this was a bit boring for you.
Yes.
Okay.
Sure.
Yeah, I'm sorry about that.
No.
I was afraid that it would be too difficult because I didn't know exactly what your background is. What about, so you're Daniel, right?
Yes, I mean, I still learned a lot of things
Okay,
that I didn't know before.
that's good to hear. But what about Salvador? Was it also too easy for you?
I mean, this was all new for me.
It was new.
I mean, the idea of symplectic and all of these results.
Okay. But the actual definition of a symplectic form you had seen already or not?
I don't think I have. No.
Okay, good. So half of the audience was not so bored or so. Was it too difficult then?
Well, it was sort of new. So
Okay, but was it very difficult or was it okay still?
it was fine, I think.
Okay. Yeah. And are you also planning to go in the direction of symplectic or differential geometry, or you don't know yet?
I don't know yet. Yeah, to be honest, I'm not sure.
Yeah. So how many different options are there in Colima? What are the options? So geometry, you can do differential geometry, number theory, or analysis?
Yes. So one of my colleagues is harmonic analysis.
Yeah.
I have two of them. I have another one who is in biomathematics.
Yeah. What about the Swiss fellow? Is he still there?
Yes, but he's in physics.
Ah, right.
High energy physics. That's his field.
Yeah.
No, sorry. Solid state.
Yeah.
Yeah. So he's still here. Yeah.
Yeah.
Christoph.
Ah, yeah. I forgot his name, but okay.
Hoffman. Yeah. No, he's around.
By the way, I can maybe stop sharing my screen, right? So